This unit is called Organic Chemistry, and honestly, the vast majority of it is looking at different compounds, or molecules, I should say, and naming it. So that sounds quite like things you've done in the past, where you've looked at maybe formulas and naming what's going on, and perhaps you need to add a Roman numeral, or perhaps you have some prefixes to add. Organic chemistry is much different than the standardized ionic and covalent naming that we've done in the past. And we'll see in this PowerPoint kind of a start to how those names actually work. So before we get to that point, let's just get a little overview of what organic chemistry is, and then we'll get into how to name things. So organic chemistry, obviously the word organic is something that you see quite regularly, maybe organic food or organic clothing, things like that. In chemistry, it means something a little bit different. So organic to us is just basically anything that's carbon-based. So we're going to see a lot of carbon. Lots of carbon chains, maybe some carbon rings. Carbon is the black stuff in this molecule here. Also, when you think organic, you probably think all natural. So you're eating natural foods without pesticides, or your cotton clothing weren't treated with any like fake dyes and stuff like that. For us, organic compounds can both be natural or also synthesized, like the fake stuff made in a lab, just so long as it's mostly carbon-based. So if we were to think of two different substances, sugar and salt, salt being NaCl, most of our sugars have a slightly different structure, but all are based out of carbons, hydrogens, and oxygens. Sugar would be our organic substance. So even though salt very easily occurs in nature, and many sugar things, like if you think like licorice and much of the stuff you find at Bulk Barn might actually be stuff that is man-made, that sugar-based stuff is actually the organic compound when it comes to chemistry. If we're looking at this, how I said the black spheres are carbons, the whites are hydrogens, and the reds are oxygens. If we were in person, we'd have model kits. We play with those. But that's a cool little diagram instead that you get to see. So anyways, why actually study it? It sounds like organic chemistry is probably a very niche science, seeing as it's mostly carbon-based, and carbon is only one element of a very large periodic table. But it actually encompasses a lot of different things. A lot of your body obviously is organic. A lot of the things synthesized in labs that you wouldn't even think would be an organic compound actually are. We'll see that kind of at the end of this section. We can look at some examples as to how we can also synthesize organic compounds to improve upon what actually occurs in nature. So one type of example is salicin. So salicin is naturally occurring in willow bark, and deer and moose did and still do use it for their own pain reliever. Natives also used it as a pain reliever. The thing is that there are side effects to using salicin, and some people, even with mainstream drugs, kind of have the same side effect, that you'll have stomach pain and nausea. So on the idea of salicin and looking at what the chemical formula and structure is of it, scientists were able to synthesize a similar compound, acetyl salicylic acid, that has fewer side effects. So still can upset some tummies, maybe not everyone's. It might sound kind of familiar, or ASA might sound familiar, just because this is the main medicinal ingredient in aspirin. So you may have seen it on some pill bottles in your medicine cabinet. So very similar structure to salicin, has a few extra atoms attached to it. We'll see it later further into the unit. Just we've been able to make something that's naturally organic better by synthesizing a fake organic, synthetic. So we can synthesize tons of different things every year. About 250,000 are synthesized a year. And that includes, like I said, a whole bunch of things you probably didn't think would be organic when we're talking about licorice on the first slide. And on this side, we can see like polyester nylons that you might wear are organic, plastic shopping bags, rubber, a lot of food flavorings, like fake menthol and things like that that you might use around the holidays. Those are all organic compounds. So let's take a little look at carbon, just seeing as it seems to be like the main element to make anything organic, right? So these are points that will just naturally come to you. So just in case this is news to you, trust me, it will be something that you just devote to memory. So all the carbons we see, they're going to make 4 bonds, and that's just because carbon has 4 valence electrons. The bonds that it does make can be pretty crazy looking. So maybe when you did high school chemistry or any high school science, maybe it was in the chemistry classroom, and sometimes you'll have molecules all around the classroom that look like completely wild, like weird spheres that look like soccer balls, massive flat sheets, all made out of those kind of model kits that we looked at with the black, white, and red spheres. We won't name anything crazy like that, but we will look at a lot of chains and rings. And then another thing that we'll see about carbon is that it can make single, double, and triple bonds. So depending on what type of bond we're looking at, how I said we're doing a bunch of different naming in this unit, we're going to be naming things differently. So we're naming a lot of compounds, like we said. We won't be doing anything ionic, no normal covalent bonding type names, but everything we'll be looking at, because carbon's a nonmetal, will be a covalent bond with other nonmetals. That brings us to what they actually bond to, and we'll see a lot of hydrogens. We already saw that. We saw oxygen on the first slide, and we were talking about sugar. The other elements that we'll probably see pop up here and there are nitrogen and the halogens. So you don't really need a periodic table to name these things. We're using a very specific small number of elements within organic compounds. And which elements are present and how those elements are bonded into our chain are called a different thing. And what we'll be looking at, calling them, are functional groups, which make different organic families. So the purpose of being able to identify a functional group in an organic family is just that they share similar properties, just like any other family, right? So depending on what kind of pops up in your molecule, you might have different properties, such as a high melting point or high boiling point. Maybe it's insoluble or soluble, will have different properties because of that structure. I already said this. And so we're going to focus on naming for now, based on those functional groups in organic families. And then our last lesson in this unit is going to be looking at the physical properties that happen because of different functional groups. So let's look at the simplest type of compounds, or molecules, sorry, which are called hydrocarbons. It's pretty much all in the name. A hydrocarbon is carbon and hydrogen bonded together, just those 2 types of elements. That makes it sound very simple, but it can get into a very complex size. Depending as well on what types of bonds we have 4 different organic families. So if we only have carbon-carbon single bonds, we're going to be having the organic family called alkanes, which is what we're going to learn about today. If we have within, it could be a massive chain, as long as there's one carbon-carbon double bond, It's no longer an alkane, it's going to be called an alkene. So instead of ANE, it's going to be ENE. And again, if we have a massive, massive, massive chain, and somewhere in there just one carbon-carbon triple bond, we'll be calling it now an alkyne, YNE. I'm going to hold off on talking about aromatics because that's going to be in the next lesson. Just know that it's a different organic family. Anyways, so just to make sure that when I name a molecule that might look a little bit strange, and that you would name it the exact same way, and a student from a different chemistry class names it the exact same way. IUPAC, the people that tell us how to name stuff, establish certain rules and methods in order to go about naming something when you can see a picture of the molecule. So one of the big points about it is what we were going to end the name with, the suffix. So if we have all carbon-carbon bonds that are singly bond alkanes, we'll learn about what the entire start of the name is, but at the very end, the last 3 letters will be ane. Ane for alkane. If we have a carbon-carbon double bond somewhere in there and we're dealing with an alkene, alkene, our suffix, the very last 3 letters of the entire name will be ene. There's a triple bond somewhere in there, we'll have an alkyne, so our suffix will be ine. So those are our suffixes. The prefixes, the start of the name, comes from how long our chain is going to be. So we have our formulas down this middle column, starting with 1 carbon, 2, going up to 10. The prefix is in this first column. The harder prefixes are actually the first ones. So meth, eth, prop, and bute. Because we probably don't use those prefixes as much as we do the later ones because they usually pop up in like the shapes we do in elementary school. Like we do pentagons and hexagons, heptagons, octagons. We know that a pentagon has 5 points. Well, penta would also mean we have 5 carbons. It's nice though that some of these names are probably kind of familiar sounding, right? Like propane, we use for our barbecues. Butane, we might use for like camping barbecues. I do not camp. Octane, you may have seen that at like gas pumps, the octane levels in gasoline. So if we have a 1 carbon chain or a 2 carbon chain or a 3 carbon chain that are all singly bonded carbons together, 3 carbons means prop, ane means singly bonded. Cool. We'd have a propane. So we're gluing a prefix and a suffix together. These are only for alkanes, remember. It would be ene if we had a double bond, ine if we had a triple bond. The next slide is going to look a lot like the last one, but we're going to focus in on these 2 columns. So what we're seeing is that when we have an alkane, we're going to have 1 carbon, 4 hydrogens. But if that methane is now an alkyl group, a branch coming off the main chain, we're going to have 1 fewer hydrogen. And that happens all the way down this chart. If we have 20 carbons for this C9, we only have 19, did I say carbons? I meant hydrogens. We only have 19 hydrogens for a no-nil once it's a branch. So you can probably read those blue words off to the side, but that's just because an alkyl group as a branch is coming off our main chain. It needs that extra bond available instead of being occupied by a hydrogen to be open in order to bond to that main chain. So we'll see that in the next slides when we're naming something. So not the biggest of deals, but just something to hone in on because we'll be looking at a lot of these formulas over and over and over again. So let's see this stuff in action. Cool. We're going to figure out how to name this molecule. So it's kind of cheated already because I've got step 1 kind of told or telling us already with this marked line around it. So step one is to find our main chain, which is the longest continuous chain. That doesn't mean that it has to just be a straight line. It can bend. So the easiest way to maybe start learning this, or the way to think about it, would be if I had a highlighter with me and I wanted to highlight without kind of going back on myself to make it continuous. So if I had a highlighter and I started here and I went to this carbon and I've got a choice, I can continue my chain and go down, or I can keep going left. I want to keep going left because I can make it longer. Keep going left, and without lifting my highlighter, I could still make it longer. That is our continuous main chain. So it can bend. The bendiness can sometimes make these really hard to name. So we've got 1, 2, 3, 4, 5 carbons in this highlighted or circled off area. If we went back, 5 carbons gives us a pent. And because they're all singly bonded carbons together, it's a pentane. So this guy right here is a pentane. We're not done naming it though, because we also have the CH3 hanging out right here, and we haven't named that. So we still have to make sure we do that. So here it is circled. We're like, hey, let's name this. So that's a branch or an alkyl group because it's hanging off the main chain, and it's 1 carbon. And so if we went back to that chart, we'd know that a 1 carbon alkyl group is a methyl. So that's what we're going to name it, a methyl. But we haven't completely named it because we haven't said where this methyl is actually coming off this chain from. Is it coming off this carbon? Is it coming off that carbon? Perhaps changing the location of the methyl would also change those physical properties we were talking about previously. Might have slightly different melting and boiling points, maybe a slightly different solubility level. So we need to really thoroughly name everything about this chain. So how do we say where it actually is? Well, we kind of have the answers on the slide, but why is that the right way to say it's a 2-methyl? So we're going to number our carbons. Obviously, that's what all these numbers are. They're numbering the carbons. And we're starting from over here because it's going to give us the lowest possible number for this branch. Meaning our other option would have been to give this carbon number 1 and name it 1, 2, 3, 4 methyl 5. And obviously 2 methyl is lower than 4 methyl. We're going to stick with 2 methyl. So we've named the chain as a pentane. We've given this all the information we can, what it is, methyl, where it is on carbon 2. All we have to do is glue that information together. It is a 2-methyl pentane. I'll talk more about how I named this with the dashes and the lacks of space in a couple of slides. That is probably a very simple one to name, and we'll get into some stuff that's much more complex. Here's a couple of ways that we can make things more complex. We can have different types of branches or alkyl groups, meaning we could have methyls and maybe ethyls and propyls all hanging off of the same main chain. If that were to happen when we're naming things, we want to name those alkyl groups in alphabetical order. So ethyl would be named first, then the methyls, then the propyls, alphabetical order. We can also have several of the same type of alkyl group. So we might have several methyls coming off of the same chain. If that pops up, we have to use additional prefixes. So if we have 2 methyls, we can use a dimethyl. We have 3 of them, trimethyl, 4, tetramethyl, 5, pentamethyl, and so on. So those are prefixes you've probably used before. Anyways, a couple of examples. If we have dimethyl, we know there's 2 methyls. and they'd be at these locations. We'd have to have 2 digits because there's 2 methyls. That's also the way we have to do it even if they're coming off the same carbon. So if we have diethyl, we know there's 2 ethyls. Even if they're coming off the same carbon, we still have to write that number 2 times, just to say like, hey, I didn't make an error anywhere. There are 2 ethyls, and yes, it seems repetitive, but they're both coming off of carbon number 2. The additional rules that I said I'd get to would be that commas separate numbers. So we saw that. There's a comma in between the 2's. That dashes separate words from numbers. Cool. We've got a dash. There's numbers on this side, words on that side. And the third rule being that we pretty much never use spaces. Everything is just this long continuous word. That's going to be a little bit difficult for you if you decide to type up your assignments, because most things end up getting underlined in red just because it's not a real word, right? But you're just going to have to, well, spell check that on your own. Anyways, so let's get to some examples. We'll try to work through them as much as we can without any of the writing on the next slide, but that writing will come in handy once we get to naming, just to see all of our information down on a page. So anyway, step 1 would be to find our longest main chain, so that part with a highlighter and not doubling back. So you can start at either side. If we want to start here like left to right, we can. So with a highlighter, we'd start going across. We have an option. We can keep going across or just duck down and make it really short. Don't want to do that. Options. We want to keep going. Options. There's definitely more if I keep going across, keep going across, keep going across. So this guy isn't twisty at all. It's just a very long main chain going right across our page. And it is 1, 2, 3, 4, 5, 6, 7, 8 carbons long. 8 might be one of those prefixes that you're used to. It's an oct. And the suffix would be ane, because these are all single bonds. So this is an octane. That would be the very end of our name. We just have to name all the branches or alkyl groups coming off of it. Cool. So all 3 of these are like those things we've seen before. CH3, that is methyl. So all 3 of these are going to be methyls. And this guy isn't 2 methyls together. This guy is what an ethyl looks like. 2 carbons long. If you wanted to check that chart, it's a C2, 2 carbons, H5, 5 hydrogens. We're just showing how it's all bonded together. So that's an ethyl, not 2 methyls. If you had 2 methyls coming off of the same carbon, that'd be a methyl group coming down and a methyl group coming up. Anyways, so we've kind of named everything, now we have to number it. So we want to know if we want to make this carbon 1 or this carbon 1, and that all rests on numbering it in a direction that we're going to hit a branch first. So if this is number 1, we're going to hit a branch at carbon 3. If this is number 1, we'll hit a branch at carbon 2. Not that much different, but better. Lower number, which means this is definitely number 1, this is number 8. We'll number everything in between. So here's all of our info. We've got our octane, we've got our methyls, got our ethyl, and now we have all of our numbers. So we have all of our information. We just need to glue it together and make a name. So if we're following that first rule, we've got 2 different types of branch. Ethyls will come first, just because E is alphabetically first before methyl, M. So we'd have a 5-ethyl at the start of our name. 3 different methyls all get grouped together in the name. We first say where they are, 2, 3, 6, with commas separating them. There's 3 of them, so we have a trimethyl. And then we glue it all to what our main chain is called, an octane. So this name should be the same name everyone would give this molecule. in our class and any class because we're all following the same IUPAC name and rules. Without looking at the second one, let's try that. So this one looks a little bit funkier, especially if you looked at the answer. It's obviously not so straight. So this might take some trial and error because you might want to go right across. But if you were to do that, you'd look at this as an alkyl group and think, I don't even know how to name that because it's not a straight chain. So let's maybe look at starting at one of these bottom carbons. I'm just going to go here because it makes it straighter for me. This would give us the same answer though if you did end up doing it. So if we started at this carbon and went up, we can pick where we want to go. We want to keep going up, keep going up, keep going up. We can go either left or right. We clearly want to go right. There's more stuff. We go right. We can go up or keep going to the right. Well, there's two more if we go up. So this would be our highlighted strip. This would be our main chain, which is 7 carbons long. If we go to that chart, that makes it a heptane. So this is our heptane. We have this that didn't make the cut. We didn't highlight it. We didn't highlight that. And we didn't highlight this. They're all CH3 groups, 1 carbon. So they must all be methyls. So we've got 3 methyls, a trimethyl on a heptane. We just need to figure out the location, the number of those methyls. So we want to know if this is going to be carbon 1 or if this is going to be carbon 1. If this is carbon 1, we've got 1, 2, 3 methyl as our lowest methyl. If this is carbon 1, we have 1, 2 methyl as our lowest methyl. So this guy is the right answer. Let's check. Neat. A bendiheptane is correct. We've got our 3 methyls labeled. There's the one we spotted out and why we numbered it this way. The 2, there's one on 4 and on 5. So that's where our 3 numbers come from, their locations, all separated by commas because they're numbers, a dash before the words. We've got 3 methyls, so that's where the tri comes from. And without any space, we glue it to our main chain name, hept, because it's 7 carbons long, ane, because all of those carbons are singly bonded to each other. Okay, but wait, there's more. So we said we could have halogens. They get some cool names. So instead of fluorine, we'll call it a fluoro. Instead of chlorine, it's a chloro. Bromo for bromine, iodo for iodine. They also get the alphabetical rule. So say we had a bromo and an ethyl group on our main chain, bromo would get named first just because B comes in the alphabet first. So these would be called the alkyl-halides because they make kind of like that salt. And 2 others, these are nitrogen based. We'll see more of them in further naming. So nitro has nitrogen and oxygen, NO2 group, and an amino. So aminos might be something you've studied before in biology, and that'd be NH2. And a few more practice ones that incorporate some of these different groups. So I'm going to go quickly through it. This is our main chain going across, and it is 5 carbons long, so it's a pentane. This guy's obviously hanging right off the end, so let's make this carbon 1. So we'll have a 1 bromo, a 3 and a 4 dimethyl. So we'd have a 1 bromo, 3,4 dimethyl pentane. Should hopefully be on our next slide. This guy, kind of simple looking because it's just straight, right? That NO2 is the nitro we had from the last slide. 3 carbons long. That's going to give us a propane. And it's on carbon number 1. So a 1 nitro propane. This one here is a little bit complex because we just did a couple that were just like straight across, right? But say we're starting here as our first carbon. We have carbon 1, 2, 3. If we go straight, we can make it 4 carbons long. But if we go up and make a weird bendy chain, we can make it 4, 5 carbons long. So we can make it a pentane if we wanted and make it bendy. So that is our main chain. We're going to call this carbon 1 because we obviously have stuff coming right off of it. We've got a 1, 1, 2 trichloro. And then on our third carbon, a 3-methyl pentane. Nice. And our last one, let's see, if we start here, 1, 2, 3, 4, 5, 6, 7 carbons. We've got ourselves a heptane. It's going to be our second carbon, so a 2-fluoro. On our fourth carbon, a 4-ethyl, because it's 2 carbons long. Ethyl comes before fluoro in the alphabet. So we have a 4-ethyl, 2-fluoro. I think we said it was a heptane, but I can't remember. Yes, good. Okay, so our answers here kind of circled out for us if we need that. And that is our first lesson for organics, and we're going to use all those naming methods and name different organic families in the next lessons.